Share my screen. So can everyone see my screen? I'm assuming everyone is muted. So hello everyone, I'm TC. I'm a PhD candidate at the Yale School of Forestry and Environmental Studies. And one of the things I work on is urban heat islands. And urban heat islands basically uh, an urban heat island is the phenomenon where a city is warmer than the surroundings. And the problem is that since you're defining the urban heat island as some kind of perturbation from some background state, we need to define both of them, the actual urban area as well as what you would consider that background state. And this is important because, as we know, more and more people are living in cities at the moment. And the urban heat island does have a lot of public health consequences, as well as its influence. Wait, let me the chat. Okay, so sorry. As well as influence on how much energy is being used for heating and cooling, how much secondary air pollution is being generated, etc. So, as I said, since urban heat islands are defined by the difference in temperature between the city and the background state, it's important to consider what would be the inconsistencies in both the urban quantification and the rural quantification. So here I'm showing a couple of shapefiles, like administrative shapefiles for Beijing and Tokyo. So the interesting thing to notice from the background satellite view is that for Beijing, you have a lot of these urban areas in the middle of the city, which of the shapefile, which makes sense, but you also have a lot of forested area. On the other hand, for Tokyo, it's almost entirely an urban like a concrete jungle. And even if you move away from the city, it still is pretty much built up. The way urban heat islands are normally defined in the literature is you take this administrative boundary, then you create this buffer, mostly an equal size, so a buffer of equal width for Beijing and similarly for Tokyo. And then you compute the temperature difference between the administrative area and the buffer. The problem is, as I showed, like the buffer around Beijing is mostly forested, while the buffer around Tokyo is more built up than anything. So it's very hard to compare these urban heat island intensities. Plus, the other issue being buffer size should ideally vary with city size, because there has been research that has shown that urban heat island also has a footprint which is proportional to population as well as the size of the built up region. So to kind of address these issues, I developed an algorithm called the Simplified Urban-Extent algorithm, all implemented on the Earth Engine platform. So the way I define urban heat island is no longer for individual cities, but for urban agglomerations or urban clusters. So in this example, you have basically a collection or a cluster of populations, and within that you have built up structures, which includes the main city as well as built up satellite towns. And all of them are put into one single agglomeration. Then you basically find the temperature of the built up pixels within this agglomeration and the temperature of the non-built up non-water pixels. And then the difference of that gives you the urban heat island. I'd just like to go through the steps. For this, I use the global data set of urban shapefiles from Schneider et al., which is a combination of the Landscan population data set and the MODIS land cover data. I used initially for the paper, I used the MODIS 500 meter land cover data, and of course the MODIS 1 kilometer land surface temperature to actually calculate the temperatures. So you start with the urban cluster boundary. This is for Northeast USA. You clip that data to the shapefile, so the land cover data to that shapefile. Then you basically get the urban clusters. So the white ones are the urban clusters and the black ones are the rural clusters. Similarly, here the white ones are the non-urban, non-water pixels. And then you basically find the temperature of these white pixels and the white pixels for the rural cases. We evaluated this algorithm against previous studies which use more buffer-based analysis, and they are in general similar, especially for nighttime. For daytime, there are certain differences, but overall, what we found is that our methods replicate the global trends and regional trends in urban heat island, but are more consistent from the physical perspective, in that we are not considering the administrative boundaries as the primary region of calculation. So, and this whole data set currently includes 10,000 plus urban urban agglomerations, and we have data for every season, so every basically month of the year, also separated into summertime, wintertime, daytime, and nighttime, and also long-term trends from 2003 to 2017 till now. And just to make this data set more easy to access and publicly accessible, we created a web app through Google Earth Engine. I can kind of have it open on the other tab. So this is just the information page for the web application, but and this is the main web app. Basically, you can pan around and see the actual urban heat island intensities for the urban clusters you're interested in. And if you look at the legend bar, you have values for, you have the layers for annual daytime, annual nighttime, summer daytime, summer nighttime, and winter day and nighttime. If you click on any of these clusters, you basically are shown what the actual cluster boundary is, which were used to calculate the urban heat island. And then you get the annual daytime, in like the mean intensity of the cluster, basically for all the cases we have explicitly considered. You also have charts showing up, which show the change over time for daytime and nighttime urban heat islands, and also the seasonal trends of the daytime and nighttime heat islands. Furthermore, if you click on like you want to export this data, you can actually get the pixel-wise data for all of these separate layers, from like annual means, wintertime means, and summertime means for each year. The last thing we have is the time slider, which basically shows you the actual extent of the urban pixels. So this is for Shanghai, China, and this is for 2017. So if you kind of go back to like 2003, you can see how much the urban agglomeration has grown over time. And yeah, so basically we developed this map and released it, and it has gotten a lot of traction from the urban science community mostly. And because of the map that was generated, I ended up using it for other applications. So for instance, I have been involved in the Urban Environment and Social Inclusion Index, which is basically an index tracking the performance of cities across both environmental stressors and also how socially inclusive they are. And one of the interesting things we found was that for urban heat island specifically, there is a lot more disparity in distribution depending on your income level. So this was a paper we published last year where we looked at, this just shows the how well the different urban-rural differentials in the normalized difference vegetation index, normalized difference built-up index, and albedo kind of account for the UHI variability within the cities. And overall, we find that this is primarily because, I mean, very strongly because of the distribution of urban vegetation. So if you have higher vegetation in one part of the city, you will generally have lower temperature. And what this means is that for the 20, so in this case, we considered a global set of 25 cities. in roughly, okay, I'm gonna explain this plot a bit more. So in this quadrant plot, so quadrant 3 means that there is very high income inequality, and that the inequality is also burdening the less affluent. And this inequality is for UHI. So UHI is burdening lower income group people. For the quadrant 4, it's that there is high income inequality, but UHI is higher for richer neighborhoods, basically. And then quadrant 1 and 2 is you have low income inequality, but the urban heat island values are higher for lower income neighborhoods for quadrant 1, and it's higher for higher income neighborhoods for quadrant 2. So what we found for this selection of cities is that for 72% of the cities we considered, the surface UHI intensity is higher for poorer neighborhoods. And this is kind of related to the vegetation fraction as well. Like if you look at the vegetation distribution within cities, generally due to both real estate considerations and also the actual population, like population distribution, which depend on other socio-cultural issues, people who are in who have lower income tend to be in census tracts or regions where there is less green space, and this has been seen in other studies. And since UHI and green space is negatively correlated, you get higher heat exposure for lower income populations. So we kind of expanded on this study more recently because we were considering a pretty random sampling of cities, and 25 isn't really a lot anyway. So we decided to focus on the US specific case. The problem and one of the issues with more physical based urban UHI characterizations and how that would be useful to policymakers is that, as I mentioned earlier, UHIs are calculated for should, or in reality should be calculated for or for physical boundaries, but that data set itself is not useful for policymakers who are interested in administrative tracks in general. So what we did for this was we used census defined administrative delineations. So the red, so this is for Minneapolis in the US, and the red part is what you call an urbanized area, and this the census tract defines as a region with a population of over 50,000. And then in the background you see the actual census tract groups, which of course the where the is the are the administrative tracts for which the census data is actually collected. And based on this, I was able to calculate the urban heat island intensity. So the rural reference is based on the actual urbanized area. So we take the non-urban, non-water pixels within the urban area as the rural reference. But then the urban temperature is basically the spatial mean of the pixels within the census tracts. And this shows the urban heat island intensity for the 497-ish census tracts in the US. And we replicated the results from this plot. I'm not showing it here, but in roughly 92% of cases, the UHI intensity is higher for census tracts which have lower income, and lower for census tracts with higher income, and that's within cities. We also looked at race. So here I'm basically showing the distribution of correlation coefficients, so like the R value between the UHI intensity for, this is daytime summer, I think. So A is daytime summer. So UHI intensity versus the percentage of the census tract, which is of particular race. So what you see here is that of all the race categories defined in the census tract data, only for the white group, you have a negative mean. By mean, I'm talking, so this is basically the Fisher, like the mean of the Fisher transform of the correlation coefficients. But what this means is that for census tracts with higher percentage of white people, you have a lower UHI intensity. On the other hand, for census tracts with a higher proportion of Black people, you have a higher UHI intensity. And this is based on for all of the urbanized areas within the US. So only among the only case where we see the negative correlation, that is higher the proportion of people, lower the UHI, is for the white group, but it's positive for everyone else. So non-white people are in general exposed to more urban heat island than white people. And the other interesting part of this is that this is for summer, right? And then you come to winter nights. And during winter nights, you would assume that an urban heat island would actually be beneficial, because that would actually reduce your heating load and it would reduce the effect of cold snaps and cold waves. But during the winter night, there is almost no significant, like there's not as much of a difference between the races. And this is also true for income. Even for income, the spread kind of becomes more normal than skewed, which means that while you get the adverse, while non-white and poorer people in urban areas are getting the adverse effects of summer daytime UHI, they're not necessarily getting the possible benefits during winter nights, which is so we currently have this paper under review, and it's interesting because it talks about the actual disparities in UHI distribution, and a lot of it is related to how vegetation is also distributed within these cities. At least in the US, the general trend is that people uh, who are richer tend to move into the suburbs. And this is, of course, a general trend. There are exceptions depending on the cities you're looking at, which is like the idea of urban flight, which used to be white flight. And usually in the middle of the city, you have generally poorer populations. And in the middle of the city, you also generally have less vegetation. And due to other reasons, even more than vegetation, higher UHI. So this is not a causal effect, but it is one of the consequences of the distribution of population and the distribution of temperatures within cities. So that's one part of it. So that's just talking about the spatial variation and how to look at the administrative versus physical boundaries when we define the urban heat island. The other part of it is that when we look at changes of urban heat island over time, we need to kind of consider the urban growth. And this is hard to do because I have already talked about how the delineations of urban and rural are hard enough at a static level, but doing it dynamically is hard because firstly, there are no good, not as many good data sets for changing urban boundaries over time. Most of the classifications were mostly done at the for multi-year means. For instance, the MODIS 2000, I think version 5 of the MODIS land cover data had changing pixels for every other pixel class, land cover class, but the urban class remained the same. This was updated in version 6 of the product. But for now, I have switched to the European Space Agency's land cover dataset because it's available from 1992 to 2018. And it's also at 300 meters, so it's at a slightly higher resolution than MODIS. So this basically shows why urban growth is important when you're looking at urban heat island characterizations. And I have a lot of these for just like showing urban growth is important because like there are like different ways to look at the same idea. But this shows the percentage growth in urban built up area from 1992 to 2015. So you see like values of 4 to 5 times the 1992 values in many of these cases, which means that if you're using the same static map for long-term urban heat island mapping, you may be getting biased results. Similarly, this is just another, this is just an animation of the built up, the top, top 10 cities, countries in the world with built up area from 1992 to 2018. So it's like a bar chart race. I saw like so many YouTube videos of, so I decided to make one. And what's interesting is that a lot of these countries are growing at a very fast rate, especially China. So these are important. And then looking at the city scale level, data of the urban pixels changing from, again, same 1992 to 2018. So particularly for Shanghai, which I keep showing every time I show that app to anyone, is how much it has changed over the last 20 years. So to do this, what I did was I created a global set of vectors from the European Space Agency land cover data. And doing this was actually much harder than I thought it would be, because that data set, like vectorizing, is in general very computationally uh, expensive. And with Earth Engine, I had to do it by country. Like I couldn't vectorize the whole like whole global land cover data set at once. So one of the issues with doing it by country is that there are certain urban areas which actually cross country boundaries. For instance, like El Paso crosses the US-Mexican border. So now you basically have two separate vectors which are adjoined. And at that time, I wanted to join this in Earth Engine as well, but for whatever reason, computationally it was not working out. So I had to actually switch to ArcGIS. So I created basically 1 meter buffer around each of these polygons, like dissolved them, and then did like a -1 meter buffer to get these vectors which are crossing the US Mexican border. So that's the first part. That's the having a consistent growing polygon set for urban areas. The next part is have for the rural references. So this shows basically the polygons for the 1992 case and the 2015 case. So not only are the actual existing urban areas expanding, you also have the addition of new urban clusters as time goes on. And that would affect how you define urban heat islands and also how you characterize them. So this is a similar, this one is for some similar bar chart trace, but for the number of urban clusters instead of the size of urban area. And this is where China overtakes the US pretty fast. Like there has been a lot of new urban clusters forming in China, and each of them in theory would have their own urban heat islands. So wait. Right. So the next step was to creating the area normalized rural references. So I'm still using, I had to kind of go back to buffers for this because by definition, my urban vectors are only include urban pixels. So I cannot do a simplified urban-extent algorithm for those vectors. So what I did was I created buffers of different widths around the clusters, and then basically I iterated over each of those buffered areas till I found the buffered area, which was roughly 2.5 times the, I think it's, sorry, 2 times the size of the urban clusters. So by defining the rural reference as a multiple of the urban clusters, you are normalizing it by the size of the cluster. And the choice of twice the area is based on previous literature looking at the actual intensity of the urban heat island and its footprint for different cities. So one of the other things to note here is that my previous urban heat island database had like 10,000 urban clusters, and this increased to roughly 840,000 for 2015 for the new data set. And this is important because a lot of these studies on global urban like global scale urbanization focus on larger cities, and that may not be a full representation of what's happening throughout the globe. So once I'm done with that, it's time to actually calculate the UHI intensity. So the UHI intensity is basically the temperature difference between this, the urban cluster itself. So this dark grayish, greenish one here, and then the rural reference, which is the outer edge of this cluster. And this is using dynamic urban-rural delineations, which means that both the urban and the rural polygon is changing over time. So for instance, for Shanghai, This is the one for 2001. So this is the urban cluster. This is the buffered rural reference. This is the one for 2018. So this is not to scale. So this has grown tremendously over that time. And then this is the rural reference. And what we find is that overall, both urban and rural pixels increase in temperature pretty similarly. The main difference, it seems, is with the tropical region, where there's a very slight increase in temperature per decade, but not really, this is not statistically significant. Similarly, if I were to now do the same thing, but with static urban-rural delineations, so in this case, I'm using the value for 2018, because generally in the UHI literature, people will use more recent administrative boundaries as the unit of calculation. So you get a much higher, like, positive urban heat island values, like roughly 1 to 2 order of magnitudes higher, which means that the way we are defining the urban and rural delineations kind of gives you different results for long-term trends. And this is important for when you want to make decisions about how projections of long-term urban heat islands. The other, I did the same thing for night as well. So similar to that, for nighttime, you get hardly any change if you're using dynamic urban and rural delineations. But when you look at static delineations, you get, again, a positive trend pretty much. And so there are two parts of to this, why this is happening. But I did some example calculations for why this could be happening. But basically, if you keep the urban delineation same for both years, and the urban, for instance, for the first case here, the temperature increases by 3 degrees for these pixels and by 1 degree for these pixels. And the same thing happens here. The only difference between these two sets is that this is static, as in the urban and the rural regions of interest are constant over time. And here is dynamic, the urban and rural regions of interest are changing over time. And you do see what is happening is because in the first case, the urban LST is increasing slower. So this is increasing from 21.25 to 23 point, urban LST is increasing, here it's increasing. For static cases, it's increasing, but for dynamic cases, it's actually going down. And the reason is that the urban area itself, the definition has changed. So now you're considering all these pixels, and when you do the area averaged value for this, you get a lower value. So this is important to looking at climatological means of urban heat islands, but doesn't tell you much about the existing, like, pixel level value. So for these pixels, you still see an increase in temperature, right, from 26 to 25. Similarly, for this, you see a temperature difference from 26 to 25. So that's where I am right now. Like, it is important to standardize these urban heat island calculations. So first, the issue of how do we define administrative versus physical boundaries of urban heat islands to have consistent ways of calculating how much an urban area is deviating from the background state, and then looking at temperature changes over time and talking about, is this temperature change happening due to the background temperature change, or is it happening due to the effect of urbanization? So yeah, I'm still kind of working on how to bring this together into a consistent summary or a story. But in the meantime, I can actually also show you another app I have been working on for the US specific study, where you can explore both the UHI and the socioeconomic data. So for instance, this shows the urban heat island intensity at the census tract level for daytime. Again, it's pretty much a copy of the other one, but I added more functionality, daytime, nighttime, and so on. And this shows the demographic data. So this is the percentage of white population. So lighter colors are less percentage. So as you move away from the city, you tend to get more proportion of white people. Similarly, for income, as you move away from the city, generally you get higher income census tracts. And it's pretty obvious when you look at these plots as well that there is this negative correlation between higher urban heat island intensity, which is, the more red it is, the higher the temperature, and the income is like a negative correlation. And this is pretty consistent across the board. Wait, what happened now? Across the board for most US cities, like, yeah, pretty much you see higher UHI intensity for lower income census tracts, and also for lower census tracts with lower proportion of white people. Anyway, so that's kind of what I have. If you have any questions, I would love to answer them. There are probably a lot of questions on the chat I haven't seen.